it's noon for me.
Well, that's true.
Yes, it's noon for me at least today. Okay. I think we are live now, right, Karina? We are good, right?
Yes. Yes.
Okay, great, great.
Good.
All right, we are ready to start. Hello, everyone. Thank you very much for your attendance today here on the YouTube channel of the Department of Civil Engineering of University of Chile. Today we have our last seminar of the international series of seminars of the University of Chile from the geotechnical group of geotechnical engineering group here. And today we are very pleased to be here with us learning. We are learning from Professor Ross Boulanger, whom you can see in the screen. Professor Boulanger, hello, how are you? How is everything back in California?
Very nice. We're enjoying blue skies, which is a good thing.
Yes, always a good thing.
Yeah.
So, Professor, thank you very much for being here with us today. We are very happy that we have the possibility to have you presenting part of your work. Just before starting the presentation, I would like to request permission from you to switch quickly to Spanish to welcome our students and the national audience of Chile.
By all means.
So we switch. Hola, ¿qué tal? Muy buenas tardes a todas y todos. Bienvenidas y bienvenidos a este nuevo seminario del Grupo de Geotecnia de la Universidad de Chile. El día de hoy contamos con la presencia del profesor Ross Boulanger de la Universidad de California en Davis, quien nos estará presentando sobre su trabajo en represas en conjunto con el tema de licuefacción. Le damos la bienvenida a todos los estudiantes, a todas y todos los estudiantes que están aquí el día de hoy con nosotros, aquí en la sala Zoom, así como a los colegas que se han ido integrando también a esta transmisión Zoom en el día de hoy, donde también coincide con la finalización de esta serie de charlas internacionales que hemos tenido durante este 2021, donde hemos contado con la presencia de espectaculares, ¿cierto?, profesionales de la ingeniería geotécnica que hacen investigación de avanzada. ¿Ya? We switch again to Spanish, English, sorry. So, continuing with the presentation of Professor Boulanger, Professor, just before giving you full presentation, we would like to ask you some questions regarding, is 3 short questions, I promised, very short questions. The first question is, what is your story? How was it to become a geotechnical engineer, and how did you get to this position in which you write a lot of publications and you work with the centrifuge? How was the story, your career?
That's always a challenging question to reflect on, how you get somewhere in life. I think every time I think back to this, it really is the good fortune of having good friends and mentors, surrounding myself with really great people. And that's really been how everything worked out for me. I came from Canada. I'm from British Columbia. And at the time that I was graduating as an undergrad, the economy was very poor. So I did what most students do, and that is consider going to graduate school. And it was Professor Liam Finn, which I imagine many people would know. And Liam Finn was very kind to me when I was an undergrad, and we had a friendship, and I went to him for advice, and he said, well, wouldn't you rather, I could go anywhere in Canada for a scholarship. I had a national scholarship. And he said, but wouldn't you rather go to California? And that seemed like a pretty good idea. And so he gave me the address for Harry Seed, and I wrote to Professor Harry Seed, and he recruited me to Berkeley, and I went south to California, and I had never heard of earthquakes, and I'd never heard of Berkeley, and I had never planned on leaving my hometown or certainly leaving Canada. And I went for 1 year, and I met my wife, who's from California, and I stayed. And then everything after that has really just been the good fortune to be around people who were extremely talented, and they were really good mentors and friends. From Lelio Mejia at what was then Woodward Clyde. He really taught me a lot when I was working for them for a couple of years in the Dams group. And then coming to Davis and working with Professor Ed Idris, who again, many of you would know, and Professor Bruce Cutter, who really is the kind of person who launched and is the genius behind all of the capabilities of our centrifuge facilities. And then, as the years went by, the colleagues that came after that, working with Jason DeYoung and Katerina, who you had talk earlier, and now we have Alejandro. There's really too many people to mention, but it's really, it's just about good friends. I'm not sure that answers your question, but I wouldn't say I ever planned anything. I just always enjoyed many things, could have taken many paths. But the people I mentioned particularly have had a big impact on my life. And then running the centrifuge facility, Dan Wilson is our associate manager. And so he and I have worked closely for the last 15 years. And he was my first PhD student from 29 years ago. And wow. Just all these different people. I think that's what makes life exciting and fun and productive.
Definitely. So after your undergrad, you in UBC.
Yeah.
You were in UBC. And then you went to Berkeley for master's or PhD?
Both.
Both.
Yeah.
Okay.
Then I went to Woodward Clyde Consultants in Oakland for a couple of years.
I see.
And then I came over to Davis in 1992. And I've been here 29 years. So
wow. Time flies, huh? Time flies. Amazing. Nice. Very nice. Very, very nice. And well, they didn't come up so short, but it's great. It's great to know a lot of details about these stories. And in what projects are you working these days? What mainly?
Well, so we, on the research side, there's lots of different subjects. We work collaboratively with lots of different people. And I think, what I really enjoy, also enjoy, different from the university is the engagement in the profession. I get the good fortune of being engaged on review boards for a number of projects. And so I was thinking about this. Currently, I'm involved in a couple of projects that are very large tailings impoundments. Involvement on a design of a new dam, raising of an existing dam, and just finishing construction on modifications to a pair of dams, which an auxiliary and a main dam. And I was just thinking of those. The other projects that I'm on that I really enjoyed recently are two soft ground tunnels involving fairly long crossings and really significant shafts on both ends. And I guess what I've really enjoyed about all these engagements is it kind of goes back to, I was just saying that there's so many talented people involved in delivering these kind of larger projects, dams and tunnels, that what I really enjoy about them is being around people who are so talented at everything from the construction management, knowing how to do plans or specs or alternative delivery methods, or the construction, all the different expertise that's required. And I really enjoy being around those people and seeing how things are pulled together on these kind of larger projects. And for the students who are thinking about their career paths, I would say that I find these areas of civil engineering extremely rewarding for the fact that you have to work in large teams on these projects, and no one person has to know everything. You just have to have something that you contribute on the team. And
exactly.
Yeah, it's been a great career for me. So hopefully all your students enjoy their careers as much as we have.
This is an out of the blue question. What would be your advice for the new generations regarding on how to become an efficient engineer? That would be the question, because probably the concepts apply regardless of the ground, right?
Yeah. Well, that's a tough question. And it's one we spend time with our students talking about how to develop oneself.
Yes.
Ralph Peck wrote a number of articles about this, and there's a collection of his papers in a book called Judgment in Geotechnical Engineering. And I find that they are often a very useful thing for younger engineers to read and just get a sense of how he approached problems. And I think maybe the way I think about it is developing your comfort with being a little more philosophical about life. You have to get comfortable with the best possible science that you can do, the best understanding of all the theories that are necessary for us to interpret what we're seeing, but then also getting comfortable with the limitations of the tools we have. So like, and how we do construction and how we can deliver projects. And so really you have to get familiar across a broad range of topics to be effective at integrating problems. So it's challenging yourself to always keep growing. Don't ever get kind of notched into doing the same experience year in, year out, year over year.
Exactly.
I think Ralph Peck said something like, if you do the same job for 30, the same thing for 30 years, you have 1 year experience repeated 30 times.
Exactly.
So keep growing. And then at the same time, you have to pick something that you can contribute to the team that no one else does. So that's finding one part of it that you're really good at and getting really good at it, so that when people need help with something that's hard, they come get you. So never shy away from learning something hard. If it's hard, it's better, because if it was easy, lots of people will learn how to do it. If it's hard, fewer people will bother learning how to do it, and you'll be better in demand. So taking the challenge of learning something really hard is actually best way for job security.
That's an awesome advice, actually. I absolutely agree. The tougher, the better.
Yeah.
Right? Yeah, I absolutely agree. And the last question, with so much geotech and so many projects, what do you like doing in your free time?
Yeah, I was laughing when I saw that coming. So my oldest daughter has two children of her own now. I have a 6-month-old and a 3-year-old granddaughter, and my wife and I, our primary focus in life right now, outside
absolutely,
of work, is being a grandparent.
Absolutely. Family first, always.
Always. Yeah. Best thing in the world.
Yes, absolutely. Wow, that's awesome. And what are their names?
Charlotte and Maeve.
I see. 3 years and 6 months.
Yeah, that's
nice.
And they are beautiful and easy children, and it's wonderful.
You're going to miss them when you go to conferences.
Well, in COVID era, I haven't traveled at all. So they live really close to us. So we see them several times a week. So
nice. That's nice. Very nice. Very nice. That's great. Great.
One upside of lockdowns, I guess.
Yes. Okay, Professor. Thank you very much for sharing all that. Really, really, really cool. Really cool to know some details about you. And thank you for sharing that. And with all that said, we will give you. I will turn off my microphone, my camera, so you can start sharing with us your presentation. Thank you very much again for being here with us. We really appreciate your time for being here. Thank you, Professor Boulanger.
Okay, well, thank you. I appreciate the invitation and the opportunity to speak here. I really have enjoyed my visits to Santiago in the past, and such great hosts, and it was such a beautiful place to visit. So I wish I could be there in person, and hopefully will be someday in the future. So thanks for the invitation. Okay, and then I had to pick something to talk about, and I was trying to think of what the students might be interested in, and I think it's often nice to think of case studies because it gives you a chance to query how well our analysis methods work against observations in the field. And so I've chosen to talk about an analysis that recently completed for the Austrian Dam in the 1989 Loma Prieta earthquake. And I'll give a little background of why I'm looking at this dam in this presentation shortly. So the first thing is that this is a dam that's about 55 meters high. So it's not a small dam, but it's not the biggest either. It was constructed in the early 1950s, primarily of clay sands and clay gravels. And so it's modern construction techniques, but maybe not as dense as a newer dam, more recent vintage dam. It's estimated to have experienced peak ground accelerations of about 0.4 to 0.6 G in the Loma Prieta earthquake. And that resulted in extensive cracking of the dam and settlements along the crest that were as great as 860 millimeters. So pretty significant. And now this dam was studied pretty extensively by the firm Waller Associates back in the 80s. And then Babbitt was at the Division of Safety of Dams in California. And then Les Harder et al. Looked at it and wrote up. So there's some good papers about the background of the dam and its performance. There's really only been one dynamic analysis of it, and that was by Vrymuth and Lamb, and they used a very simple Moore Coulomb-based model. So not one of the more conventional or current, more modern models. And so a few comments about this. When we look at doing numerical analyses, a key part of that is the constitutive model that describes how the soils will behave. And in particular, the options for modeling compacted clay fills like clay sands and clay gravels in practice are pretty limited. And what you see is that it's fairly common in practice for people to use total stress, kind of elastic, perfectly plastic models, like Moore Coulomb-based strength models, or sometimes hysteretic models, which are also total stress. And these types of models do not simulate some key features of how these kinds of materials can cyclically soften, generate pore pressures, or accumulate strains under earthquake loading. So these simpler models don't really look like soil behavior. They get some of the key things like strength, but they often miss some of the other aspects. Now, there are some advanced models that have been used, for example, some by Mejia et al. And Elia and Royania, but these kinds of models are not common in kind of our practice, particularly North American practice. Now, that leads to kind of an interest in developing and validating these kinds of models and then analysis procedures for practice. And at this point, I'd point out that the additional motivation for this study is that the Austrian Dam is in an area where there are several other dams of similar size, similar vintage, constructed from similar boro materials. And so they have a lot of common characteristics to the Austrian Dam. And those dams are all in reevaluation for seismic loading behavior. And so the motivation was to take the kinds of analysis methods and tools that we're using in our practice and applying them to the Austrian Dam as a way of checking or validating that our procedures are consistent with what we saw this dam behave like in that earthquake. And so it's testing our methods that we're going to consider using on these other projects. So that was the motivation for the study. So what I'm going to walk you through is to kind of illustrate all the pieces of this is I'm going to walk through a two-dimensional nonlinear dynamic analysis of the dam, walk through how we characterize the embankment, and here we will be relying on existing data, some isotropically consolidated undrained traxial compression data, some anisotropically consolidated cyclic traxial test data, some resonant column test data, and some of the construction field data. So we're going to use all the existing data. We'll do the analyses using a program that's popular in our practice is the program FLAC by Itasca. And then the constitutive model we're going to evaluate is one called PM4 Silk. It's a plasticity model for silk that myself and Katerina Ziotpopoulou put together just a few years ago. I'm going to run through the analysis cases, and I'll show you alternative ways of calibrating the model, different input motions, and several other sensitivity analyses. And in this regard, anytime we do these analyses, the important part of the analysis is the insight into what matters and how the response can vary with uncertainty in the input parameters. So you always do a sensitivity analysis. If you ever get an analysis that just says, well, this is the predicted displacement, that's at best a missed opportunity, and at worst can be potentially misleading. So I want to show some of the sensitivity analyses and insights we get from that, and then just kind of conclude on whether or not these methods appear to work well for these types of conditions. So that's what I'm going to walk you through. If you're interested in some of the details, they're all available in a paper that came out in our geotechnical journal 2 years ago. And if you're not a member of ASC, you can get a copy from my UC Davis homepage. It is behind a link to a page called Only for Friends, and the password is friends. And so you can get a copy there if you're interested. With that, I'm going to try and not go down into too many details during the presentation to keep the time maybe a little tighter, but want to highlight some of the key points particularly for students coming up into geotechnical engineering, kind of the range of things we have to do for this type of analysis. So the first thing we got to do is step back and look at how the dam behaved in the earthquake. This is a view of Austrian Dam. The spillway is over here on the right-hand side. That's the embankment dam. You can see the reservoir is low because you can see the bathtub ring. In fact, the reservoir was low for the 3 years prior to the earthquake because of an extended drought. And so we're quite fortunate that the water levels weren't really high. So that's what the dam looked like. And then after the earthquake, you can see some, this is a view looking along the crest, looking towards the left abutment. And you can see cracking and damage all the way down the paved road that comes up the crest. And what you had were longitudinal cracks on the upstream and downstream faces. They are up to about 100 millimeters wide, and they went as low, deep as a little over 4 meters on the upstream face and downstream face, like here, longitudinally. On the abutments, there were transverse cracks, and these cracks were up to 200 millimeters wide, 3 meters deep out here in the embankment. And if you got over at the contact with the left abutment, they were up to 450 millimeters wide and 8 meters deep in certain locations at the contact with the abutment. So there were significant cracks. On the right-hand side, where the abutment is against the spillway, this is the spillway wall, concrete structure, and you can see that there are cracks and separations, again, up to 250 millimeters wide, up to 7 meters deep. So extensive damage all the way along this embankment. On the toe, going near the bottom of the dam, there was bulging and cracking of the face of the dam. So the embankment was slumping and extending out at the toe. And this is a map just kind of summarizing what I showed you. There's the crest of the dam along the top. That's the spillway over there on the right side. There were zones of cracking on the upstream and downstream face near the crest. There was bulging near the toe, and then there were transverse cracks on the left and right abutments. So that's kind of gives you the pattern of deformation. There were settlement measurements across the crest that were taken. So this is the crest elevation measured along the station along the crest. The crest is about 250 millimeters long. And it was measured only a couple days before the earthquake, or a day before the earthquake, and then a couple days after the earthquake. And the difference between those two is the crest settlement. And that gives you about 750 to 860 millimeters of settlement over the central 200-meter length of the embankment crest. So the whole center section's slumped about 800 millimeters on average. And then measurements that continued over the next week showed that there were no further deformations with time. It looked like it moved during the earthquake and then held there in time. So that's what we're trying to see if can we predict that kind of response. Now, in addition, there were some piezometers at the site. And the piezometers are shown here on the cross section of the embankment dam. Again, the reservoir was low because of the drought. And there were a set of piezometers, pairs of piezometers at these three locations. And the water level in the embankment had come down and stabilized because of that sustained lower water level. So we know where the water level was. Right after the earthquake, they went out and measured these again, and the water pressures in these piezometers showed excess pore pressure rises of between 3 and 17 meters of extra piezometric head. So there was a significant pore pressure generation in these materials. Those were monitored for a couple of weeks after the earthquake, and they dissipate very slowly, which makes sense because it's a clay, sand, and clay gravel material with low permeability. And that suggests that the pressures right after the earthquake were maybe anywhere from 0 to 10% greater. So we think the piezometer records are pretty indicative of what happened in the earthquake. Okay, so now that's how the dam behaved. Now we're going to look at the motions that we think it experienced. And this is the surface projection of the fault plane from the Loma Prieta earthquake from Wald. And the epicenter is here. Austrian Dam is right there, and it's on the up dip side of the projected fault surface. And Austrian Dam is about the same distance from the epicenter as the Corralitas station. So there's recordings here about same epicentral distance and about the same position relative to the fault plane. And so that looks like a pretty good candidate for an input motion. And the Lenihan Dam is located a little bit further from the fault surface and from the epicenter. And it's, closer to Austrian Dam, but a little bit further from the source. So it's also a candidate. Now the Lenihan station is on Franciscan Formation. It's a sandstone, siltstone, claystone, gray wacky, which is like a clay sandstone. And it's all can be very jumbled and distorted. And you have an inferred shear wave velocity of about 1,000 meters per second, which isn't particularly high for rock. Austrian Dam, we have no direct geophysical measurements at it. It is on the Franciscan Formation. And from other measurements in the area, the bedrock velocity could be anywhere from 760 to maybe 2,700 meters per second. So that's kind of what we see in the Franciscan. Over here at Corralitas, the site's actually on a large landslide massive landslide. And the shear wave velocity measured there is a little lower, around 460 meters per second. So neither site is a perfect match for Austrian Dam, but they're reasonable for estimating the motions. So these are the recordings. The Corralitas station is the one, a similar kind of source distances that we like. These are the acceleration records. Corralitas channel 1 is actually aligned in the direction, the transverse direction of the dam. So Corralitas channel 1 is probably our best representation of expected motions at Austrian Dam. And then the Lenihan Dam has slightly different characteristics. And you see the red and purple here shown over on the right in response spectra. And the red and purple, they have lower peak accelerations at lower periods, or spectral accelerations at lower periods, but they're richer at longer periods. And that could be the influence of the abutment and the dam at the Lenihan site or not, so that there's some uncertainty in the motion. So we're just going to run all four. I'm going to do most of the base work with the Coriolis channel 1 is kind of our best representation. So now we've got the motions. Now we're going to characterize the dam. And then in the cross section of the dam, I'm not sure I quite showed it, so I'm going to jump back here and tell you that the dam was zoned as having an impervious upstream shell and a pervious downstream shell. But the difference between the pervious and impervious zones was based on selective borrowing during construction, which means that just during construction, they would tend to place finer grained material upstream and coarser material downstream. Underneath the downstream shell were these gravel drains. Now they're not continuous, they're strip drains. And so they're spaced apart. And so in between the strip drains is just more of the shell itself. So the drains are just there to bring the phreatic surface down. So if I jump over here, the sampling and testing of the upstream shell gave you this range in blue for grain size distributions. And the sampling on the downstream shell gave you the orange range. So a lot of it was very similar. Sometimes you were a little bit coarser with a little less fines, but more samples were in the higher fines content range, such that in the end, the two zones of the dam are almost the same. You can't really tell them apart from the boring samples or from the construction records. So for all intents and purposes, the dam is essentially homogeneous. In terms of characteristics, the dam classifies, the materials classify as sandy clays and clay gravels, kind of a mean of 32% fines, passing the number 200 sieve, and those fines have a plasticity index of about 13. So slightly plastic clay, sands, and gravels, which are difficult materials to characterize. And that was a challenge. So what Waller did was they took tube samples. They were larger diameter. Some of them were 15 centimeter diameter samples. They took those samples and they did ICU tests. And these are showing the Traxo test results, stress versus strain on the left. And on the right is the stress versus mean effective stress, or the stress path on the right. And the blue tests start with a consolidation test stress of about 1 atmosphere or 100 kPa. And the red ones start at a little over 200, and the green ones start at a little over 300 and say about 70 kPa. Those stresses were intended to be close to the in situ vertical stresses where those samples came from. Now, when you look at these test results tell you that these samples are disturbed. There's some challenges in interpreting the data. These stress paths go strongly to the left in the beginning, and that tells you normally that we'd expect that path to come off a little more vertically. And this is an indicator of sampling disturbance. So you want to get used to spotting those kinds of challenges. Then you look at the stress strain response. The stress strain responses are all strain hardening. They're incrementally dilating at larger strains. And that is hard to constitutively model. So in practice, even if you were doing just limit equilibrium, equivalent static analysis, nothing dynamic, just needed the strength for a static factor of safety, you have to decide how to pick a strength off of this. And a common practice is to do it one of two ways. One is to pick the strengths at what's called the point of maximum stress obliquity. And what that amounts to, if you look at this blue line here, this point right there is where you get the largest effective friction angle. And that's fairly common in our practice. And so these points halfway up these curves are these points over here to the left, and they're in the range of 3 to maybe 5% axial strain. So one definition of the strengths is taking them at about that 3 to 5% strain. Second approach is to take them at 10% axial strain. And that means you'll only get that resistance if you actually get that kind of strain level. And so we're going to have to check those. In fact, what we're going to do is 2 calibrations. We're going to use strengths from about this range of strains. And the calibration number 2 will use the strength at 10% axial strain. These strains are about 25% greater than these strengths. So it's a significant difference in strengths. Okay, I'm also going to just point out that these are axial strains. So later I'm going to show you shear strains. And so those are equivalent 1.5 times that for undrained loading cases. So this is like 15% shear strain, and this is like, say, 5% shear strain. We'll keep those numbers in our mind as we go along. So then the next thing is we're going to pull those strengths off. And just very quickly, what we're doing is this is calibration 1. We'll pull the peak effective strengths off from that point of maximum stress obliquity, and that's what's labeled here, peak stress ratio. And then this is a way that we kind of like to plot strength envelopes. And so this is from Lamb and Whitman, where this point is the radius of the Mohr circle at that failure criterion. This is the center of the Mohr circle at failure criterion. So you don't plot a Mohr circle, you plot the top of the Mohr circle. And then you're looking at points instead of circles. And it's easier to put a fit through that to get a strength. And then those convert back to the equivalent failure envelope C prime, cohesion intercept, and effective friction angle phi prime, just using this transformation by Lamb and Whitman. So it's a nice way to kind of look at strengths. So I thought I'd show you that. And what we get is this stuff. It's gravel with the matrix filled with clay fines, but we're getting a peak effective friction angle of like 43 degrees, which for a well-graded dense material makes sense. You then turn around and you plot in the bottom the undrained strength, tau FF, so that's going to be the shear resistance in the undrained test, plotted versus a consolidation stress. So sigma FC prime is the sigma prime on the failure plane at consolidation. Same thing, you plot just points, not more circles, and you fit them. And this is a notation by Duncan, Wright, and Wong, and it's very common in dam engineering practice to use this representation. The intercept is called D, and the slope is called psi. And this way we relate undrained strength to consolidation stresses. So we're using that notation. This is just showing you that we repeat the process for calibration 2, and that's larger strains, you get higher strengths. And then summarizing them, these are in the paper, and it's just giving you the undrained strengths for consolidated isotropically ICU conditions, or this is anisotropically consolidated to the highest possible stress ratio possible. And again, this is common in our practice, Duncan, Wright, and Wong. And then we use these two envelopes to interpolate strengths for anisotropically consolidated strength conditions. So if you're interested in how we do that, those details are provided in that paper. The key I want to point out, though, is picking strengths for this strain hardening material is fundamentally challenging regardless of your analysis method. And you have to decide what failure criterion you're going to use to define strengths at. So we're going to do these two different calibrations. We also had some cyclic traxel tests. These were very sparse data, though, and they were performed at 3 different consolidation stresses, 2 different anisotropic consolidation stress ratios, using samples from both the upstream and downstream shell, and only doing 9 tests. And then the lines in between them are the inference of what the trends and patterns are. We largely follow what Waller did, and they give some bounds on what we think the cyclic strengths would be. We do think these are affected by disturbance. So for the same reasons that I talked about before, there's certain things you can look at in the responses, including the reconsolidation strains when they're consolidated in the lab. The strains were fairly large, indicative of sampling disturbance, which it's really hard to sample gravelly materials without disturbance. Okay, there were also some resonant column data. This plots the small strain shear modulus. So this gives you like small strain stiffness, which is directly related to a shear wave velocity. And we have these measurements, these 4 points, plot them versus mean effective stress, and you get a relationship that describes how strength or stiffness goes up. The slope is this parameter n. If you're in sands, we're used to stress going, or modulus going up as the square root, 0, p prime to the power 0.5. So this is like the square root of stress. But the data supports something closer to about 0.6 as an exponent on that. And so we did both, but I'm going to show you the results for the solid black line. So we fit the small strain modulus. And what this does is this corresponds to velocities of about 370 to 540 meters per second in the shells. And those are pretty consistent what we see in similar materials at other kinds of embankments. But we don't have the measurements specifically in the field for this dam. Okay, so that's the field data. Now we're going to do the analysis and walk through how we calibrate the analysis. So first thing is we're going to use the program FLAC using PM4 Silk as a constitutive model. And one of the issues we have to decide is whether we're going to include the bedrock. Now, if the bedrock is a lot stiffer than the embankment, you might just omit the bedrock and treat it like a rigid base, in which case you have no compliance in the bedrock. Another possibility is if the bedrock's not that stiff, you include the bedrock, and now you have some kind of compliance from the bedrock, and you put in a compliant boundary, a reflective boundary, so that the waves can come up the base and then reflect back out the bottom, and then you have free field boundaries so that waves can propagate out the side too. So we're going to do both of these cases. The PM4 Silk model, just some quick background. It is a critical state and stress ratio based bounding surface plasticity model. It was developed for plane strain so that it runs more efficiently and quickly in 2D analyses. It's not for consolidation problems, so it's intended for seismic problems. And if you're interested, the manual, some example files to calibrate the model, and the dynamic link library are posted openly at our website, and you can grab a copy and play with it. There are a lot of parameters typical of these types of constitutive models, but there are 3 that a user normally uses. And the 3 are getting the undrained strength at critical state, the small strain modulus parameter that you calibrate to fit your in situ shear wave velocity or small strain modulus. And the 3rd parameter is your adjustable contraction rate parameter that you adjust to get your target cyclic strength ratio. Most people will only use these 3 parameters. And I say that there are 20 other parameters. So there's lots of other parameters. Common concern, if you've seen these models before, a reasonable question is, well, how do you calibrate all those models, all those parameters? And it's a very reasonable question. And the way you get through this is realizing that we have a large body of empirical data on how different materials behave. And so the model has been calibrated. We provide a default calibration so that the behavior produces typical responses. And we show those in the manual so you know what you're getting. And then the user focuses only on the other 3. And I like to, the analogy is when you drive a car, you use a gas, a brake, and a steering wheel. You've got 3 things. There's a lot of other things going on with the computer controls of all the engine and everything else inside the system. Someone else has done that calibration for you. And then you just worry about your 3 components as you drive the thing. And that's really the intent of the model, is to make it usable in practice. So you get reasonable behaviors and you focus on the 3 input parameters. Then I also want to elaborate on how you use these models, because kind of going to our earlier discussion, how you think about these problems or develop yourself. And I'm going to advocate for students as you're coming into this, is you think about separating the task of characterizing soil from the task of constitutive modeling. And try not to conflate the 2. And the reason I'm going to say is, if you're going to characterize the soil, you need to characterize the soil whether you're doing limit equilibrium analyses or dynamic analyses. It's your job to decide what data you trust. And so you're going to estimate those properties maybe several ways, and you're going to use the best ways available to you. And when you do that, you're going to find that the data that you have is going to have inconsistencies. If you try to measure strength two ways, you will get two different answers. And you have to decide which of those approaches gives you a better, more reliable estimate of strength. Same thing for modulus or any other parameter. So everything we do to measure properties is flawed. You need to learn the limitations of those tools. And then when you use multiple tools, figure out how you're going to select your properties given those inconsistencies. That's got nothing to do with constitutive modeling. Then when you go to do your analysis, you're going to pick the input parameters of your constitutive model to make the model give you the properties you picked for the analysis. And if you decide to emphasize a certain set of data as being more trustworthy, a constitutive model will not resolve inconsistencies that you have in your data. So don't be surprised if you have inconsistent data, don't be surprised your constitutive model won't match both sets of data because they're fundamentally incompatible. And I'm going to show you an example of that. And that's what makes these models both challenging and fascinating to work with. So just a comment on the calibration process. Step one is we set the parameters that we're going to fix for the rest of the iterations, like undrained strength we've picked, small strain modulus, we picked those numbers. We know the void ratio that we're going to use on average. We then take the model and with single element simulations, model monotonic undrained loading and check that you're getting what you want for a stress strain response. Then you simulate strain controlled cyclic undrained loading. And again, we have these calibration files, we call them drivers, on our website. So you can use those to do this. And you simulate those. And there's a parameter H0 that you can adjust to adjust the stiffness, which means you get different secant modulus over small strain modulus ratios, this G over G max ratio. Likewise, H0 will affect the monotonic stress strain response. You're going to have to decide which one of those two to emphasize. Then you simulate the cyclic undrained loading tests. And again, you can adjust it. This is a different parameter, the contraction rate parameter. So you get the kind of number of cycles to failure approximately correct. There are three other parameters that with a little practice, you can tweak them. And we tweak them because we know the model well enough. We tweak them to get better estimates of shear strain accumulation as obtained in those tests by Waller. And then you repeat these steps, and you just usually, after anything, with a little practice, you get better at it. And usually you can calibrate this model within 2 or 3 hours, for a given set of data, because you go around the loop maybe once or twice. So it gets pretty quick. In the paper, we give you a list of all the parameters. There's the set of default values listed for all the different input parameters and what they mean. We'll go through all those details. There's 2 calibrations where the dash line says we just use the default. These are the numbers we tweaked. These are the 2 that we changed for contraction rate, and they have 2 different strength models. So that's the differences. And this is the rest of the parameters. And so again, lots of parameters that I think after you get used to using it, it's just like all those things under the hood of your car. If they're not hurting you, leave them be. Okay, so how does the model behave? Next thing is, anytime you use these models, you need to show what they do and check. Don't trust that they're doing it. Check, confirm it. So this is showing stress versus strain. And from the stress versus strain, these are loops at different strain magnitudes, and it's showing the secant modulus versus strain amplitude, and normalized by small strain modulus. So this is G over G max. And this is calibration 1 on the top and calibration 2 on the bottom. Calibration 1 is the solid symbols, open symbols are calibration 2. And you see the 2 calibrations give the identical G over G max, and on the bottom, identical equivalent damping ratios. Now, what I want to point out is the hard part is knowing what you want to get, right? So the blue line here is what you would expect based on Vucetich-Dobry's correlation for fine grained soils with a PI of about 15. That would match the matrix material for our shell, that PI 15 fines portion. The red line is what you would expect for non-plastic granular gravelly materials. And that's from Menck with Stokey. And for a similar coefficient of uniformity for what we have at our site. Now, that's what you'd expect for the gravel. That's what you'd expect for the matrix. So what do you get if you mix the two materials and you have, clay gravels? We don't know. And so we'll go down the middle. And that's just one of those uncertainties that we live with. Now, this is showing then the monotonic undrained loading responses, just showing what you get for strength. And I'm showing here is deviator stress versus strain. And this illustrates a common problem for these analyses. That is, this is like showing a wart so you can see that you have to deal with this. So don't hide it. Put it on the table and deal with it. And it goes like this. On the left are stress strain responses from two tests at a confining stress of about 100 kPa. And the two tests at that confining stress are the blue tests. The same material, same samples, or samples from the same shell. And so you have some variability in the strengths you're getting at that stress. Calibration 2 gives us this orange line. Calibration 1 gives us that straight line. And that's because we fit strength data, and now we're modeling it with our relationships for strength. And this illustrates that you don't actually get the stress strain responses. We get a range of strengths. And because they were calibrated for smaller strains and larger strains, you get a difference. But we are not modeling the strain hardening response. To our knowledge, we haven't found a model that does that yet, and that's something we need to keep working on. Second thing I want to point out is this stress strain response. The lab data are really soft. Now, you can make the constitutive model softer and model that, but to do that, you would have to lower the small strain modulus Gmax and make the G over Gmax behavior really soft. In effect, if you take this blue curve and you bring it back here, it would produce a G over Gmax curve that is way over here to the left and makes no sense. And so, in fact, we know that these samples are disturbed, and we know that the disturbance really breaks down the small strain stiffness. So you have to make a choice. Do you trust the small strain modulus data and G over Gmax correlations, in which case you get very stiff simulations? Or do you trust the monotonic data? And if you model the blue curves, then you get really low dynamic properties. And you get to pick. Now, for our practice, we trust the shear wave velocity measurements that we get in the field, and we trust our G over Gmax data better than we trust the stiffness from monotonic test results. And this just illustrates the constitutive model doesn't make that inconsistency go away. You have to make a choice. I will tell you that if you put this really soft modulus in a dynamic analysis, what happens is we often we get like no excitation of the system. We underestimate responses. So we know that we don't like to use those in dynamic analyses. We underpredict observations from those. And the ones on the right are for tests at the higher stress. They show the same kind of conflict. Now, I'm going to keep an eye on my time here. This is showing cyclic responses, just to show how the material behaves. This is with no static bias, so you get stress strain loops. If you put a static bias on it, strains accumulate downslope. And the stress paths on the right. These are showing cyclic stress normalized by consolidation stress. So it's just showing how we get different cyclic strength curves versus number of cycles, depend on failure criteria. This was all for calibration 1. This is showing for the same calibration how you get different strength curves depending on confining stress. That's just because undrained strength varies with confining stress. So that goes along with it. And this one shows that if you take the cyclic strength and normalize it by undrained strength, they collapse to what we see empirically is it only takes one cycle to fail something if you load it at its monotonic strength, and then fewer cycles if the loading is a fraction of the monotonic strength. So this is consistent with what we see empirically. And this is calibration 2, just to show we get the similar kind of response out of calibration 2. The only thing that's different calibration 2 is the monotonic strengths are about 25–30% greater than calibration 1. So now I've got to jump ahead here. And the thing is, there's lots of details that go into the analysis. So we'll get to the analysis results and they go pretty quickly. First, we need to get the initial stresses in the embankment. So we're going to model the seepage conditions. We have piezometer levels, so we calibrate the constitutive model to the piezometers. If we put in measurements, permeabilities, we don't actually match the piezometers very well. So you end up having to tweak the hydraulic conductivities and their anisotropy to match the piezometers. And in fact, this piezometer is lower than these ones down here. And that illustrates the complexity of probably layering in the dam, seepage through the bedrock we're not modeling, and other challenges. But we're getting the saturation levels about right on average. This is just showing that we also check that we have smooth contours of vertical effective stress, smooth contours of initial coefficient of earth pressure at rest, K0, and smooth contours of the initial static stress ratio, just to make sure we don't have any unusual stress concentrations or problems, and that the numbers look reasonable. This is just turning around and plotting whatever the undrained strengths we put in, which again follow this Duncan, Wright, and Wong procedure. We then just take those strengths and express them as a ratio of overburden stress to just see what kind of strength ratios we're implying within the model. And not surprisingly, at large overburden stresses, these strength ratios are down in the range of about 0.4 because they're getting to be like normally consolidated materials at these large stresses. And then at shallow depths, you have higher strength ratios because they're the compaction-induced stresses. Materials are more like they're over-consolidated relative to their overburden stress. So everything works out, makes pretty reasonable sense. So I'm going to do some nonlinear analysis now. Okay, we got all the pieces, we put in the motions, we do it, all what we mentioned. Here's our first one. This is our calibration one, the weaker calibration, which will make sense in a minute. The Coriolis channels, we're using channel 1, that was our preferred motion that is aligned along transversely to the dam. Motion 2 is the vertical motion, so we're including the vertical motion in the analysis. This is the input motion from Coriolis, channel 1. This is the response at the crest. You see we get strong amplification, and then the crest rings for a longer time after motions, exactly what we'd expect. We see the dam crest movements during the duration of strong shaking. So this is displacement in time. We see we get a little over a meter, so a bit over 1,000 millimeters of settlement. And then this is showing the pore water pressures at 2 of the piezometers. And so we're getting pore water pressure divided by unit weights of water that are 10 to 20 meters of excess head after shaking. Compare those to the piezometer records in a little bit. Okay, so then we look at deformation patterns. These are horizontal displacements. The upstream shell is moving towards the right by amounts of up to 800 millimeters. The upstream shell is going upstream about the same magnitude. The symmetry of the dam gives us a symmetric slumping of both shells, where you get a couple things worth note. These are strong gradients in displacement right here, with this point not moving and this point moving 400 plus millimeters. This is a zone of extension. And that's exactly where you see the tension, longitudinal tension cracks along the face of the dam. So it's right where you'd expect it. Same on the upstream side. You see the strong gradients in displacement at the toe. That's where we see bulging in the field. And then you see crest settlements of a little over 1,000 millimeters, which is pretty close to that 859 that was measured after the earthquake. These are the shear strains. Maximum shear strains down here along the bedrock are on the order of 10 or 15% strain. So that's a little higher than is assumed for calibration 1. But at the same time, the majority of the embankment is in the range of strains that are consistent with that calibration. So calibration 2 would have been more consistent with these strains, but overestimate strength for these strains. So the 2 give us a chance to kind of see if we bound the behavior. The bottom figure is excess pore pressures. And in this whole green zone down here, your excess pore pressures are on the order of 10 to 20, or 10, That's 100 to 200 kPa, which is about 10 to 20 meters of piezometer rise. So throughout that zone. Now jumping ahead, this is calibration 2. Calibration 2, strengths are about 25% higher. Those higher strengths give smaller displacements. Crest settlements are now smaller, which makes sense, right? A little stronger, a little less deformation. These are the strains, a little less strains, and a little less excess pore pressure with the stronger calibration. Now I'm going to summarize these as we go along, lots of details here. But what I'm summarizing in this table are the measurements first. These are the accelerations at the base, and these are going to be the crest settlements. And what we measured was 859 millimeters. If we use Coriolis channel 1 as the input, calibration 1, the weaker strengths give us 1,060 millimeters. The stronger calibration gives us something maybe 20% less. But those two numbers are in the range of 859. And then if we change and use Coriolis channel 3, we get about the same result, even though the motion is got a significant difference in some of the spectral features. If we switch and use the Lenihan motion, for calibration 1, we get about 20% less displacement. And for calibration 2, we get about 20% less. So there's about a 20% effect between the calibrations and a 20% effect between the two different sets of ground motions. But if we're predicting 600 to 1,000 millimeters, and we're measuring something like 860, this is pretty good because that tells us, given all our uncertainties, we're at least bracketing the response. If we check the pore pressure transducers, these are the piezometer rises at 4 different locations. And these are the measured values right here. I'll note that this point over P6 is where the piezometer is, but because our saturation levels are right at that piezometer level, this point B6 is a little lower in the mesh, and the pore pressure response is vary quite a bit. So just to show you that just a little bit deeper in the mesh, what the results change like. With calibration 1, you see all these pore pressure heads are about 15 to 19 meters, and they're pretty close to measured. These ones are more like 7 to 10, bigger than measured. These are about 10 to 4. These are larger than measured. And then these are smaller, but a little lower in the mesh, we're getting bigger. If we go and use the next one, the stronger calibration, all these piezometer heads come down a little bit, but they don't go away, which show that this bound of strengths gives us both reasonable predictions on displacement and also a reasonable indication of the excess pore pressures that developed in the embankment. We did a number of other sensitivity analyses, including changing the modulus in the embankment, changing polarity of motions. We took the input vertical motion off and on. We increased the saturation levels up into the embankment, which has kind of some compensating effects, so increasing the zone of capillary rise into the embankment. We had some difference in unit weights. We just checked that. And then the big one down is bedrock compliance. All these other ones were in the range of modest changes, 10 or 20% at most. So a lot of them just a few percent. None of them made a big deal. The bedrock compliance was a bigger issue. And if the bedrock is somewhere between 1,000 and 2,000 meters per second, we would have got 20 or 30% less displacement. And so getting the bedrock compliance and site-specific measurements would have been valuable if we could have. But the displacements, even though they're smaller, are still in this range of 750 to 867 millimeters, which is again in the range of the measurements. So we feel like we can continue to bracket the responses. So I'm almost done, and I want a few comments on some of this stuff. So the first discussion point. Okay, so I was racing through all the different parts of the analyses and then just kind of throwing through some of the analysis results. And I think, for the students, if first time you're seeing some of this, or maybe you've seen it before, but the details, you're still getting maybe used to them. In that case, I want to point out that the real challenge in there is that we were doing a lot of different steps to do this analysis. And so when we talk about the validation of an analysis method, a nonlinear dynamic analysis method, that the validation doesn't just apply to the tool. So what we just did, it wasn't just the constitutive model PM4 sand, and it wasn't just the use of FLAC. It was how the user used those two. It's how you calibrated those models. It's the choices one makes when you run the numerical analysis, whether you put in a compliant bedrock base or don't put in a compliant base, or transmitting boundaries, how you initialize the initial seepage conditions. Big ones are, how did you pick the properties? What were the target calibration properties? So the whole way of characterizing the site, the geology, the stratigraphy, the properties, all of that is an essential input to the analysis. And then your specification of the loading conditions, hydrologic and seismic, are major considerations in the results. So it's all the inputs and all of the package that produces the output. And so when you calibrate or validate a process, you have to think of it as the package. Because if you change the user, just the user, you could change the results by a lot if that user starts playing with different ways of doing their analyses. So the whole package is important. And one of the things that we have a concern with in our industry is getting consistency across engineering firms doing the same kind of work. And what we're pushing for and making progress on is getting a higher degree of expectation for documentation. And Mike Beatty and I wrote a paper about this for a conference, and it's proven quite useful. We provided a checklist, and it's a checklist that we use when we are reviewing people's work. And what we're trying to get is everyone to document their results in the kind of full detail that would allow someone to recreate them. So don't hide the warts, show everything. And what that does is it allows us as a community to be more consistent and advance our kind of best practices. And that's important if we're going to have confidence in using these tools. So it's not just FLAC or PM4 Silk, it's the set of procedures that we used. And then if you think about whether in the analysis we have bias or uncertainty, dispersion in our results, all those things I just listed, from the properties to the motions and all the procedures and protocols, affect your potential for bias, high or low. And in fact, when you look at a case history study, what you're checking is the aggregation of all those steps. And if you do that and you produce outcomes that are consistent with the observed results, I want to point out that you can get good agreement by doing a lot of different things wrong. So get a little wrong here, but wrong the other way there, and they can compensate. And you can get poor agreement because you have a bunch of little errors that add up and they accumulate. And really what we need is comparisons over lots of cases, so we get a sense of just how much these range of procedures, whether or not we're bracketing responses or whether we have a tendency to be high or low. And so this is why we like to keep analyzing different case histories every time we're updating our tools, so we can see if the new tools, new procedures stay consistent. So you always keep validating it as you change the way you do your work. Last comment here is that on the compacted clay sands and clay gravels are a tough material to work with. They're difficult to sample, they strain harden, they're hard to numerically model. You have uncertainty in strengths from disturbance, path, loading rate, stress history, partial saturation, age. All those things are not really well known. And so what I was showing you was procedures that are common and representative of how our current practices do. So they could all be improved. And what we're trying to do is use two strength representations to represent the uncertainty in those strengths and give us some sense of the sensitivity of the system response to at least some measure of uncertainty and strength. So this is an area that could use some work. Just to close out, the dam was repaired and modified. The upper part of the dam was excavated down through the extent of cracking right up to the abutments. And then it was reconstructed. There was grouting done at the abutment contacts and under the spillway. And then 3 or 4 years later, they came back and built a new spillway. So the new spillway is over on the left abutment now, and the spillway was removed from the right abutment. And so the upper part was rebuilt with filters and drains. And so it's in a lot better shape. And the whole purpose of all that, concluding, is that, first of all, what we got were responses, from this set of nonlinear dynamic analysis and tools and the procedures that we were using, we got reasonable agreement with what we saw for crest settlements, embankment deformation patterns, and excess pore pressures. And when you put those together, and the fact that we could bracket the responses with various sensitivity studies, we feel that gave us confidence that these tools and procedures could be used in the evaluation of similar types of embankment dams, which, as I mentioned, is something that was on the agenda to be done. And with that, portions of the work that I'm describing were supported by the California Department of Water Resources and other portions through the National Science Foundation. And as always, that support is always appreciated. So, Felipe, I'm open for any questions if anyone may have some.
Professor Boulanger, thank you very, very much for such a great presentation. Let's see if we have questions. It seems to me that we have questions. Actually, we have some questions here on YouTube. We have one question. Well, we have many. The first one is from Nicolás Villanueva. He asks, since the PM4 Silk and PM4 Sand models are formulated for 2 dimensions, do you think it is possible to calibrate them using triaxial test data and plots?
Yeah, no, it's a good question. Yeah. And so, yeah, and so let me back up. And I'm going to go back to this picture, and I'll explain something. In the traditional kind of mechanics approach to calibrating of a constitutive model, that we would be drawn by our training that you would have a triaxial test, and it's an axisymmetric problem, and you would take your constitutive model and you would make it axisymmetric, and then you would calibrate the model parameters so that the stress strain and stress path responses match that triaxial test. And that's not really tractable in engineering practice for these types of problems. And the reason it's not tractable is simple things like, let's see, where did I put the strengths? I can't remember where I put my strength results. I think I had them back here. So which one would you calibrate to? This traxial sample or that traxial sample, or this one or that one or that one. And if you're looking at cyclic strengths, which one are you going to calibrate it to? So you're going to have variability within the lab data that you're going to be trying to calibrate. So where did I put that thing? Right here. So that's one, is that if you pick your model parameters that match one traxial test, it'll never match a second traxial test because you have variability between traxial tests. So you're going to be stuck one way. You're going to be modeling one or modeling the other one anyway. Second thing is a couple corrections. If you do traxial tests and they are isotropically consolidated undrained, well, in the field, they're not. So we will, for field conditions, we'll consider that they're, say one-dimensionally consolidated at some K0 condition. So it's common for us to take traxial strengths and correct them to equivalent field strengths, like if this was a sandier material. And you want to calibrate the constitutive model to the traxial test, or do you want to calibrate it to your equivalent simple shear strength? If you use the constitutive model and calibrate it to the traxial test and say, there, I'm good, you're relying on the constitutive model to predict the conversion to simple shear. You've relied on it, and that might work, but for some models it won't. And so you can't abdicate that responsibility. You have to check that you not just get the traxial, but you get the simple shear. And then I got to throw one more in there, and that is real loading is 3-dimensional. So you have longitudinal loading. And so we take the traxial results and we usually knock the strengths down 10% for the out of plane loading. So that's what I mean by, you would take all those traxial tests and you would put them together over here on the left, and you would pick what you want for cyclic strengths. You would pick how you want to correct them to simple shear, and you'd pick how you correct them for three-dimensional loading. And then you're going to pick what your target strength is, and you're going to allow for sample disturbance or anything else. And after you set your target strengths, yeah, then you can calibrate PM4 sand or PM4 silk to what you picked was your target strengths. Given that, you're not modeling any one traxel test, you're modeling the characterization you got from it. And then lastly, you can still look at the strain accumulation rates and determine, are the lab tests telling me that this stuff accumulates strain slowly, or does it accumulate it fast? Does it strain soften? Does it strain harden? And you can use that general information to calibrate the constitutive models. That was a long answer.
No, but a very, very interesting one. Regarding those aspects, well, I will ask at the end. Let's continue with the questions better. Thank you very much. Let's check with Nico. Nico will probably tell us through the chat of YouTube if for sure that answers the questions of Nico. Jorge Llanes. Jorge León, perdón, Jorge. Saludos para Jorge. He asked, why do you say that the sample disturbance affects negatively the cyclic strength? Is it possible to have some sample densification due to the disturbance?
Yeah, there is. Just going back to the there's several indicators that we would look at. So the first one is when you tube sample something and you bring it to the lab and you extrude it and then you reconsolidate it, you always report the reconsolidation strain in the lab. And there are various indices of sample quality versus reconsolidation strain. And the reconsolidation strains, they're given in the paper, and off the top of my head, I remember they were like 1, 2, 3% volumetric strains. They were large volumetric strains. And if the sample had retained its in situ structure very well, we would not have expected those kinds of volumetric strains. Okay, so that's an indicator of sample quality. Now, what does it do to cyclic strength? I think the question is a good point, is that you could suspect that because the sample got denser due to reconsolidation, it could get stronger. And that's quite possible. That's kind of like the discussion of whether you do an NGI type procedure or a Shansep type procedure for soft clays, right? You have to decide the trade-off. But if to the extent that there was any breakdown in fabric or the age of this material, it's sitting in the ground for the last almost 40 years at that point, would it have developed some stability that sample disturbance destroyed that more than offsets the densification? So in all fairness, I don't know which one would dominate. So that one's kind of, it just increases the likelihood that we don't know what we have. And the third one is when you look at the stress paths. Now, the cyclic task data from the 80s, they didn't show well, they don't have digital data, and they didn't show the details of the stress path in a way that you could interpret it well. But the monotonic ones did. And monotonic ones for isotropic ICU tests, traxel compression, the QP path should come almost vertical off of the P prime axis, because at small strains, you're closer to elastic, and the stress path for elastic loading should come nearly vertical off the axis. A little variation from verticals could be anisotropic, but when it comes off the axis with a strong incline, that's an indicator something isn't quite right. I don't know. Did that one make sense?
Yes.
Okay. So it's kind of all those things together. In our experiences, disturbance is usually bad for strong materials.
Okay. Thank you, Professor. Thank you. Well, let us know, Jorge, if that would answer your questions. It seems to me that it does. We have another question from Andres Torres. Actually, there is another question from Jorge. Sorry. that would you recommend to calibrate the stiffness response rather than the monotonic strength in the soil?
Yeah, we routinely do. We've seen this in many projects, and we also like when we're dealing with softer silts and softer clays, we like direct simple shear tests, and so we'll often have Traxel and simple shear. Simple shear in particular is known to give a very poor measure of initial stiffness. Mm-hmm. And so if you, and in fact, any conventional test device like a conventional Traxel or a conventional simple shear, I mean, it's well known that and well established that you can't measure small strain modulus with these devices. And what happens is you have compliance in when you're trying to measure strains at 10 to the -6 or 10 to the -4% strain, the compliance in the gears or the bearings, the threads, the frictional force on the bearings for the loading rod, all that throws stress strain response like terrible. So you need to measure stresses, loads and stresses, and deformations inside the cell and preferably locally on the sample in order to get moduli reasonably well. And we see this is a common problem. And we tend to trust small strain modulus in the field from shear wave velocity first. Then the G over G max appears to, the literature suggests that it's fairly robust because lab tests on samples, the G max comes down, but the G over G max is not too bad. That's not strictly true, but it's not too bad.
Yeah.
And then we worry about the use of conventional strength tests, Traxel or simple shear, for getting the initial stiffness. And we always find that there's a big disconnect between those two.
Yes. I was just here. I would like to embrace the opportunity to ask a question because you showed some shear strain curves along with the degradation. Those shear strain curves were obtained from resonant column. So you have a resonant column that can track all the process during the cyclic or only at certain points?
Yeah, I was kind of going quick, so maybe I did. So the resonant column tests that Waller did were just small strain. They're just resonant column. And there were no stress strain curves from them. There was only a moduli.
Okay. Perfect. Okay.
And then the response where I showed stress strain loops was purely numerical simulations to check that the constitutive model or to calibrate the constitutive model to match what we picked as a target G over G max behavior. And then, like I said, when you're thinking of, I think I had that in here, when you're looking at something like this, what target do you want? Do you want to do the fines? Do you want to match the gravel, or do you want to match the monotonic tests? Yeah. You pick, right?
Yes.
And no matter what you do, the constitutive model is not going to resolve that inconsistency for you. The constitutive model will only, you can match one of them, but you can't get both. And that characterization issue exists whether or not you're using a range of tools for your stability, dynamic, or deformation analysis.
That's a very interesting point, actually. Yeah. Thank you very much. Yeah, because I thought, my God, what a resonant column is that? It seems like a great resonant column. The one showing the entire curve, the loops.
Yeah, no, a little misleading on that one.
And so now the question of Andres Torres. There are many questions, Professor. Maybe
I got nowhere to go.
Okay. We have Andres Torres. When were the field settlements measured? Do they include the post-liquefaction consolidation? Did the simulation include the post I think that's the question. Those two. When were the field settlement measured?
Yeah.
And do they include the post liquefaction consolidation?
Right. So there's a couple parts to that. So the field measurements, fortunately, all the instruments were measured or recorded the day before the Loma Prieta earthquake. So it's just good luck. Now they were being recorded on regular intervals, and they were changing significantly every month. So they were pretty stable. But for good fortune, October 16th, the day before the earthquake, is the baseline recording of all the instruments, piezometers and displacements. After the earthquake, it took 2 days to get out there and take the readings because, well, there's a lot of chaos at the time. And these recordings were measured October 19th, 2 days after the earthquake. Then those measurements were recorded again, I think 2 or 3 times over the next 4 days, and then again later on, and they never increased in any measurable way. And so the movements were dominated by the earthquake and not by reconsolidation, which is kind of interesting. Now the piezometers, they were also measured a day before and 2 days after, and then the piezometers were monitored for 10 days after. And so some of the piezometers showed the decay of pressure in time. Some decayed very slowly and some decay a little bit quicker. And if you take those decay rates and project them back to the time of the earthquake, you just would get a few % change over that 2 days. So there was very little consolidation, we think, in the first 2 days. Next thing is, as they consolidated over the next few weeks, settlements did not go up. So reconsolidation didn't do much of it. And in the analyses, I never mentioned it, but we ran some of the analyses post-earthquake reconsolidation, and the numerical model gives you just an extra 1% strain. So it also shows not significant amount. Although that constitutive model is not particularly structured for that type of analysis, we did check that it was consistent with it.
I see. Okay, thank you. Thank you.
But we wouldn't call it liquefaction. That'd be my last point.
Yeah. Rafael Iglesias, he asks, good evening, Professor, and thank you very much for your time and the presentation. If possible, I would like to take this chance to ask you a more general liquefaction question. So, Chile is the most seismic country in the world. Nevertheless, soil liquefaction in low plasticity, fine-grained natural soils, he would like to emphasize the issue of natural soil, was barely observed in the 8.8 magnitude earthquake of 2010, and neither on the 8.4 magnitude earthquake of 2015. What would you say may be the reason for that?
It's a very good question. It's a loaded question. So the observation that ground failure in fine-grained soils, plastic silts or clays, even of modest plasticity, are less common than the effects of liquefaction in non-plastic, sands, silty sands, and whatnot. And that applies pretty broadly, worldwide. And there's a couple different reasons that I think you can understand why that might be the case. It's kind of a mix of lessons as you go along. So, but at the very least, natural deposits. Let me just back up. Like a natural deposit of anything with a modest amount of plasticity in a silt or clay, a normalized undrained shear strength ratio is SU over vertical consolidation stress might be something like 0.22. A natural deposit almost always has an apparent over consolidation ratio of like 1.2 or 1.3 just from secondary compression in the age of the deposit. And so we routinely, your undrained strength ratios in a natural deposit of silt that's just been there, 1,000 years, a few thousand years, your undrained strength ratios are, often 0.25. And if you take an undrained strength ratio of 0.25, your cyclic strength under earthquake loading is now still back down around 0.22. Compare that to what you get in a really loose deposit of hydraulic fill sands or loose alluvial deposits, where cyclic strengths, for given overburden stress and magnitude and whatnot, but for magnitude 7.5 and overburden stress of 1 atmosphere, et cetera, a cyclic strength might be down around 0.1.
Easily, yeah.
So
even
when you think
less.
of a fault source, there is a huge area that feels motions in excess of 0.1 G, enough to trigger liquefaction in loose materials. But there's actually a smaller area that's loaded enough to produce strong yielding in a plastic fines with an SU ratio of 0.22, say. So there's a smaller area that gets loaded enough to yield. That's one. Second thing is they tend, unless they're really sensitive, they can take a fair amount of strain without ratcheting the same way a sand does. And in some ways, these nonlinear analyses often can show you that the problems are not as bad as what happens is this: as you cyclically load a deposit of fine-grained soils that you described, you can get yielding at one point, but the yielding also drops the motion. And as long as the material isn't sensitive and brittle, the amount of ground movement you get is usually not so large. So, we often see the problems are when you have shallow foundations, heavier buildings on them, slopes, that's where we tend to see the problems with these materials. But out on flat ground, yeah, you just don't see the problems as much. I'm not sure that's helps a bit.
Yeah, for sure, yes. Yes. We have more questions. Okay. I think we don't have many questions now. We have two colleagues here in the Zoom room that would like to ask questions. The first one is from Jose Antonio Abel, whom I think you know.
Okay.
Antonio.
Ross.
Hello.
How's it going? Nice to hear you.
Yeah, how are you doing?
Yeah, here it's been enjoying your talk a lot. So,
it's good to see you.
I won't take much time. So I wanted to ask, pick your brain a little bit on 3D effects.
Okay. I like that beard.
I know it's not related to the case study necessarily, but what's your intuition as to what crest lengths the 3D effects would kick in? Which ones would you be worried about? What you would do with constitutive modeling? Like maybe a broad answer on that. And in 3D modeling of dams, what I've found, but I don't know if there's if you've seen evidence on the literature, the 3D models have there's this effect that when the input comes from the side waves, they converge at the middle of the crest, and there's an increase in response at the middle of the crest. So it's like this traveling wave that goes along the crest.
Yeah.
So have you seen any evidence on that? And what are your thoughts in general on that?
Yeah. So there are certain projects where 3D effects do become really, they can be critical to making a decision on whether you need to remediate or modify the dam or not. So yeah, 3D effects do come up, and the options for modeling them are less well developed, but there are some. FLAC has the P2P model, which will do 3D, and other people they'll switch and they'll do the 3D. So let me back up. You asked if there's evidence of that behavior, and yeah, I think there is. Drawing blanks on which ones to cite, but I do remember some papers on dynamic analyses of wedge-shaped dams that were analytical, and I'm trying to think, it was Gazetas was one of the co-authors. I remember they were very insightful about exactly what you're saying. And they gave kind of good insight on terms of what the aspect ratio of length to valley shape, where the effects would be more significant than not. And so I think there is some body of data to support what you're saying, or have pointed out. So that makes sense. When you go to then analyze whether it's important for a structure, that often depends a bit more on the details of the structure. And then that if it's a well-behaving structure, then it's not usually an issue because the 3D usually will make it better. If it's a really poorly performing structure, we're seldom willing to let 3D analyses stop us from doing remediation. So there's really kind of like, but there are cases where you get into, and one in particular that I reviewed, I thought the consultant did a very nice job on, was that the dam came down and there was a narrow channel at the bottom with the alluvium that would liquefy. But it was in a narrow channel. If you did a 2D section, you predicted this big movement. But if you did a 3D model, it was isolated enough. You didn't get the movement. And they did a 3D analysis, and they didn't have P2P or any of the other models at that time. So what they did is they just did the 3-dimensional model using more Coulomb models. They said if the liquefied material liquefies, we'll just give it the low strength. And they did a 2D section of it and then 3D sections of it. So it really was kind of a parametric study to get the relative effects of the geometry given a simple constitutive model. And they showed that they could lose a lot of strength in that lower layer, and the strength of the overlying layers would really diminish the deformations that developed in the embankment. And yeah, everyone thought that was a pretty convincing argument. So that's a workaround. And then what was your other part of your question? In terms of constitutive model options, you know, and when would you do it? There's other problems like ground improvement, where 3-dimensional geometries where we need these tools. And so we're working on, we have a 3D version in beta for FLAC or for our PM4 sand, but we want to exercise it a little longer before we give it out, just because we want to make sure it's robust. And Murray Kippen did that just this last year. And then the task has the P2P. So there are options to do it. The challenge is always runtime. And so, but I've seen people do it. I don't know. I'm not sure I'm answering your question, Jose. That's a tough one.
Yeah, no, I know. I just wanted to pick your brain and, you know, see what you would say regarding 3D effects. That's it. My impression too, that it's a tough thing. So it's, yeah. It's one of the things that you can bring up, but it's mostly academic. So
well, you know, it mostly, but not always. And it's one of those things, you know, there's a lot of, we get away from a lot of problems by saying, oh, I did these cases and it didn't matter, and it didn't matter, and it didn't matter. Most things don't matter until they do. And exactly. Then when they do, you wish you had the tool. So I'm agreeing with you. I've run into several problems where I really wish we had made our model 3D. And so that's Katerina and I and Marie made a 3D beta, and it's because there are problems we ran into that, yeah, in hindsight, we should have done it that way, because it does matter sometimes.
Yeah. All right. Great.
Hey, it's good seeing you.
Same here.
Thank you, Antonio. Thank you. Good to see you.
Good to see you too, Felipe.
You call him Antonio. I just knew him as Jose.
Jose Antonio. All right. We have the last question. Okay. The questions are from Gonzalo Corral. Gonzalo, please turn on your mic.
Okay, I'm here. Thank you, Felipe. Thank you so much, Professor Boulanger. How are you? Thank you.
Good to see you.
It was good to see you. It was a great presentation. Very, very interesting topic, by the way, and very important to be used this in practice. So I have a couple of questions that I have in my mind when you were showing your results. And the first question that I had was what do you do with basically with the compaction effect in your model itself? So because usually we build these dams, we build by layers, right?
Yeah.
Depending on the materials itself, sometimes we pick, I don't know, 30 centimeters, sometimes 60 or more. And that affects, of course, the K-naught value.
Yeah.
You
Yeah.
have. So what do you do in practice, or what have you done in this case in particular, or in other cases?
Yeah. Yeah, that's a good question. So they're all good questions. So that's just me stalling for time to think about what I'm going to answer with. So there's a fair amount of work has gone into estimating lateral stresses from compaction, and the work that I'm familiar with, and I'm not saying this is all of it, but the ones that I looked at years ago for the purpose you're talking about were George Fils at Virginia Tech, and then Ray Seed, who was my advisor at UC Berkeley. His thesis was with Mike Duncan on compaction-induced stresses. So I remember the papers and stuff from Duncan and Fils and Ray Seed on this. And to my understanding, of the way I recall or interpreted what they did, but if you think of the contact stress from the kind of vintage compaction equipment that we use, whether it's a 5 or 10 or 20-ton roller and the number of drums and whatnot, you can calculate what the kind of contact stress that you're getting from those materials. And that's kind of like giving you a pre-consolidation stress when you're compacting the material and you're getting a lock-in of lateral stress. That once you get down about 10 meters of overburden stress, maybe 15 meters, the weight of the soil will start to effectively diminish that over-consolidation effect, those locked-in stresses. And so they have plots of the compaction-induced stress decreasing with depth, and it's going to depend on the equipment, the material, and whatnot. And what we see that this kind of makes sense with other things we see is like looking at this embankment here. Now, this is a clay, sand, and gravel, and it was a tough material to characterize. But there are other embankments in California, similar section, but the materials were more like sandy clays. And in those materials, what you would see is if you measured undrained strength down the center of either the embankment or of a core, if it had a clay core, you'll often see the strength profile for a core, clay core, drop to like an SU over sigma V prime ratio that's something in the range of 0.3 or 0.35, which is a lot like a normally consolidated material. And that drop is down at that range of like 15, 20 meters. And that kind of goes with the idea that the overburden has erased the effects of the compaction equipment. So going to your question, when we initiate the model, we think in terms of wanting our initial stress conditions. Let's see, where do I have it? I get down here. When we do our initial stress conditions, in the bulk of the dam, we'll want to get that K0 to something that we think is reasonable, like 0.5, 0.6. And then we'll accept higher values at shallow depths. Now, in this particular case, they come up, this orange is between 0.4 and 0.6, and then the yellow at the shallow depths. We didn't chase it very low, and it's because this was vintage 1950s dam, and the compaction equipment wasn't very heavy.
Okay. Yeah, and take it, use of that figure itself is also called my attention to have a K0 so high at the edge of the slope.
Yeah,
having a number of number 2, it's in practice, it's also very difficult to compact at the edge.
Yeah,
it's very difficult.
The high K0s at the edge of the slope are easier to understand if you look at the full stress state. In essence, what you have is at shallow depths, you have the strong shear stress of the slope. Mm-hmm. And you're more like the horizontal stress is becoming the principal stress. So like if you go in active pressure, Ka for active pressure, let's say that can be like a quarter. Well, in passive pressure, it can be 4, 1/4. And so it really depends on, as the principal stresses are rotating, whether your principal stress is more vertical or getting more inclined. As you get near the face, the principal stress is getting so inclined that the horizontal stress is getting bigger than the vertical stress.
Okay, but here we are talking about the K naught. I mean the sigma horizontal, the effective horizontal value over the vertical.
Yeah, and like I said, right near the face, there are shear stresses, right? There's still shear stresses, but this ratio of K naught isn't showing you the effect, that the presence of those other stresses.
Of the yeah, correct.
Right.
Correct.
So if you pull out some of these elements and look at the total stress state, then you can understand why you're getting these higher K naught values.
Okay, Professor. And my last question is that, and of course, the model itself, the PM4 for Silk, use an initial void ratio, a constant initial void ratio, right?
Yeah.
In the whole model, did you consider just one value for that?
Yeah.
Okay, because in practice, we know that we have a variation, an important variation. So maybe,
Yeah.
Do you recommend to do like a sensitivity analysis or maybe a probabilistic analysis? Or what we should have in mind to do that, to take into account that effect? And also having the same, using the same question, if I understood properly, you mentioned that somehow you calibrate, I don't know if by hand or something like that, but the hydraulic conductivity in order to have a better agreement with the readings of the piezometers.
Yeah.
So also that in somehow needs to be in agreement with the void ratio in somehow. So,
Yeah.
So well, was my last question, and what we should do with all of this.
Yeah,
good question.
Also a good question. Okay, so so there's I think I heard like 3 parts. I want to try to tackle this in 3 parts. So the first part about is spatial variability, and you may have seen that I've been very fond of doing spatial variability modeling with several of our recent PhD students, and Jack Montgomery and Nick Paul, and I got Patrick Basal doing it, and with Chris Croggy. So there are certain times where spatial variability is like super important to understanding deformation patterns and behavior, particularly in natural deposits. There's no doubt this embankment dam has spatial variability in it, but it's nowhere near the spatial variability where I would expect it to dominate the behavior. In part because the way the dams are constructed, you're placing the lifts longitudinally, so you're very unlikely to get lateral continuity of weak, strongly correlated weak layers. So I don't think spatial variability would be like a dominant concern for this embankment. So that was one question. The second one is the question on void ratio it comes up, and I think it's a chance for me to go back to emphasize the idea of separating characterization from what we're trying to model. So let me say, for example, if you were trying to get fundamentally, if we think of our fundamental soil mechanics and we have a critical state line, well, nothing is more important than the void ratio, right? Because the void ratio will dictate where you are relative to that critical state line. It has a huge effect on strength. So fundamentally, yes, void ratio is very important. Now, if we go down a deposit of soft clays, natural deposited clays, water content can vary all over the place because the plasticity can vary all over the place. Every season of deposition, you can get a different water content, a different PI. So you'll get local variations in plasticity index, water content, and void ratio. Every one of those layers will have a different critical state line. And what really dictates the strength is the position of the void ratio to the critical state line, which is, we're fortunate, if you do a CAM clay model, and you do a CAM clay model, that's the simplest theory to kind of explain it. You get an SU over P prime ratio that's a function of your consolidation stress, not a function of void ratio. Doesn't depend on the void ratio. You could, if you change the void, you change the intercept of your critical state line, you move it up, normally consolidated, you'd move them both up. It's just the spacing between them. So you don't need to track the void ratio. We'd focus on what really matters is the strength ratio, SU over consolidation stress. And so even though void ratio is fundamental to the behavior, in the application, we realize that the variability in void ratio and the variability in critical state line go together, and we're better off working with SU ratios. Okay. Which brings me to the slide here, that the way we built the model is as in engineering practice, you're going to do all the ways you want to measure undrained strength, including if you want to measure void ratio, critical state line, state parameters. You do anything you want, but you decide what the undrained strength is. After you decide what the undrained strength is, we give that to the constitutive model. Now, it's not strictly a constitutive parameter. What we are doing, and it's explained in the manual, is whatever void ratio you gave it, it is positioning the critical state line so you get that undrained shear strength. In the way our model is formulated, if you give it, let's say you specify this value of undrained shear strength, if you change the void ratio, it doesn't change your strength. And the reason is the model will move the critical state line. If you move the void ratio up 0.1, it'll move the critical state line up 0.1. It positions the critical state line so that the answer you get is the undrained strength you want. So that's separating the modeling. The way we set the math up is different than fundamentally what the material behavior is. And that's separating that so that in practice, we'll measure, for softer silts and clays, we measure undrained strength. We'll do tube sampling and lab testing. We might do track fill. We might do simple shear. We might do vein shear in the field. We'll put the CPTs through it, and we'll all check it with strength ratios. And you put it all together and you decide what strengths you're going to use. And then in the way the PM4 is formulated, then you just tell it what strength you want it to give you.
Okay.
I find that much more tractable for practice, because you don't want to abdicate your responsibility for strengths to a constitutive model. You own it. And that way, when you run like you do a limit equilibrium slope stability analysis, and you just get a static factor of safety, method of slices, you will have done that with some assumed strengths. When you then go and do a FLAC analysis, you want the strengths to be consistent with the limit equilibrium model. That way, when you get a different analysis result, it's not because you change strength, it's because you're now doing a continuum analysis and not limit equilibrium. So we like to maintain control over the properties.
Perfect. Thank you so much. And the permeability, about the hydraulic conductivity.
Oh, on that one. I'll try to remember these. Let me get over to it. We first did the analysis. So I first point out the analysis ignores the bedrock. And the reality is seepage in the bedrock can be important. And it's really hard to predict because it's going to be dictated by all the joints and shears. And the permeability of the bedrock undoubtedly varies along the length of the embankment because joints and shears and other variabilities. And this Franciscan formation that we have is badly distorted, jumbled material. So the permeability is extremely hard to map or predict. Now with that, when we ignored in the analysis, we put in anisotropic permeabilities. So the horizontal is bigger than the vertical. And I think I said it originally twice for both all materials. And then we made the downstream shell 10 times more pervious than the upstream shell. And you run the seepage analysis and it does not match the piezometers. So then you have to ask yourself, are the piezometers wrong? Or is my idealization of the fact I'm ignoring the foundations, I'm ignoring what could be, as you pointed out, some spatial variability in the embankment. The finger drains in the gravel along the foundation, an interesting side thing, the owner went out and dug trenches to confirm that the drains were there, and they weren't all there. So there's some question of whether all the drains were constructed. And so maybe one was omitted in one location, couldn't find it. And then maybe in construction, there were some layers that were a little more pervious, variations in the boreal source, and or you have joints in the foundation. So anyway, in the end, the answer is we made the shells in the upstream and downstream shell are much closer to similar hydraulic conductivities. We dropped the conductivity in the toe drains so that they didn't draw the water down lower than we're seeing. And we had to increase anisotropy. I think we ended up making horizontal permeability like 10 times the vertical. We had to do 2 or 3 things to match the piezometers. But to me, this is an example of I'll take the piezometer data any day. Okay. Because there's the uncertainties in characterizing the stratigraphy is, control the result. So we always make our seepage analysis honor our piezometers.
Okay, thank you so much, Professor Boulanger. Thank you so much.
Professor, we are going to complete 2 hours. I told you sometimes we get very, very, very into it, and we just don't realize how time flies. See?
Well, you did warn me, and as you can kindly tell, I enjoyed the conversation, and I'm not really good with short answers, so it's my own fault too. So
no, it's really nice. It's really great. For next year, we're going to have a coffee mode, so we can talk with a mug of coffee to enjoy. It's already, yes, exactly. It's 2 hours sharp of seminar. What a luxury to learn from Ross Boulanger about the nonlinear analysis of dams. It's well, here in Chile, it's a particular hot topic always, and I think we have some more questions that we can address them by email. I have questions myself, but I can write you an email also. We really appreciate the time you took to share with us. We appreciate your background too. It's very nice always to see the centrifuge, and we came to the end of the seminar. I mean, thank you very much, Professor. It's been great.
Thank you for having me.
2 hours of Ross Boulanger. What a luxury! And we have had a lot of excellent and long seminars. And again, thank you, Professor, for being here. We appreciate the time to all the attendees that came here, not only in the Zoom room, but also in the YouTube channel of our Department of Civil Engineering. And this is the end not only of the talk, but also of the series of seminars of this year 2021. So thank you again, Professor. Probably I will be telling you thank you many times. And probably we'll see each other very soon in a conference. And we hope to have you here in Chile. The person, Ross Boulanger, here with Caterina also here in Chile. So thank you again.
Thank you.
On behalf of University of Chile and the Department of Civil Engineering and its group of Geotechnical Engineering, right? We appreciate the last words from Jose Antonio Abel and Yolanda. And we say bye. Thank you very much. We stay here offline for a little bit, and thank you. Thanks, everyone.
Thank you, guys.
Thank you.